maximum average power transfer. And this is something that you did in circuits 1, and we're just going to generalize it for circuits 2. So just recall from EE223. Try that again. Let's recall from circuits 1. That you can have, let's say you've got some sort of power source. And of course, any source, any power source, any real world power source has some Thevenin equivalent. So here's our Thevenin equivalent. And I'll just wrote this off here to show you that this is the part that we can't control. This is what we're given. If we could control it, Jesse, what would you like R sub S to be if this was a perfect power source? Can you chat? Yeah, there we go. 1 kilo ohm. Well, that's a good general guess, but no, if it was 1 kilo ohm, we would be limited on how much power this could deliver. So let's say, just as an example, to make it more specific, let's say we've got this 1 ohm load, and this Vs, let's just pretend for a second, is going to be 1 volt. Ideally, you'd like that 1 volt to appear across that 1 ohm, create 1 amp of current flow, which will give you 1 volt times 1 amp, which is 1 watt of power. But that RS is getting in the way, and that RS is limiting that voltage. And if that RS was, say, hypothetically 1K, it would drop almost all the voltage. And now you'd be only limited to getting about 1 millivolt across this 1 ohm resistor, which would create 1 milliamp of current all the way through, which would create only about 1 microwatt of power, like a millionth of what you'd like. So try again, Jesse, and tell me now what you'd like RS to be if this was a perfect source. Yeah, that's right. It's 0. It's supposed to be 0. So you would like it to be 0. And the powers that be have handed you something that's not 0. In a car battery, this RS might be only 1/10 of an ohm. And if it was 1/10 of an ohm, then the short circuit, the maximum amount of current that the battery could provide would be 12 volts divided by 1/10 of an ohm, or 120 amps. Most car batteries can provide actually closer to 500 amps. So most car batteries actually have a equivalent series resistance of 0.02 ohms. That's pretty small, but the difference between that and 0 is huge, because if it was truly 0, the car battery could supply a city with electricity. So here's what we're given. We're given this source that we can't control, and we're given some sort of load resistance over here. And this is what we want to power. Maybe this Thevenin equivalent is for an AA battery, and you want to construct a load that will allow maximum power transfer to go from this battery, from this admittedly imperfect battery, this AA battery, which has an equivalent series resistance of about 1 ohm. And you want to power whatever your new iPods are, your AirPods, for as long as possible. And the question is, what should RL be to dissipate the maximum amount of power? So, Kyle, what would you say R sub L should be to dissipate the maximum amount of power?
I would say R of L would be around
Would you like to be really high, really low, in the middle? If in the middle, watt? Is it good to have it 0 ohms? Is it good to have it infinity ohms?
I would just say infinity ohms personally.
You'd say what?
I'd say infinity ohms, just infinite ohms.
Yeah, okay. So, and let's see what happens here. If R sub L equals infinity ohms, it's like an open circuit, then we know that power for a resistor, if this is a DC value, this is because we're back in circuits 1, is equal to current times voltage. So Kyle, just finishing up, if R sub L was infinity, what could you tell me about the current that will flow?
If it was Wells infinity, there would be really any current flow whatsoever.
There'd be no current. And so there, because I would equal 0, what can you tell me about the power?
Power would be 0 as well.
Power has to be 0. Okay. So we're going to do a limiting argument, just like we did with Pavel. JT, let's do the opposite argument. Let's let RL equal 0 ohms. Now we're going to maximize the current through everything. But what can we say about the voltage across our load?
0.
Got to be 0. And so once again, if you make this 0 or if you make this 0, either way, we're going to have 0 power. So to maximize the power delivered to our load resistance, it's got to be between 0 and infinity. Does anyone remember what it is from circuits 1?
Doesn't it have to equal the, what's it called? R sub S right there?
Yes, exactly. RL equals RS. That is the answer. Not RS factorial, just RS. All right, so when that happens, you could then figure out what the current is and what the voltage is, multiply them together to find out how much power is being dissipated by the load. I'm just going to tell you. When that happens, P max of the load is equal to the square of the voltage source divided by 4 times what that resistance is. Now, the big question is we're asking, what's RLB to dissipate the maximum power in the load? If we were interested in what would RLB to dissipate to cause the generator, V sub S, to generate the most power, it would always be a short, because then we'd have the maximum current flowing. And we'd still have V sub S across our voltage source. But we're in the mode of being a circuit designer here. We're trying to figure out, given this battery, what should our load be to dissipate the maximum amount of power? And if this was a AA battery that had an R sub S of 1 ohm, we would want our load to look like a 1 ohm load. Anything else will make it dissipate a non-maximum amount of power. Now in circuits 2, we're going to generalize that. In circuits 2, we now have the rule is slightly different. It's now, this is a sinusoid source. This is a impedance. Here's our load, which is also an impedance. And to dissipate maximum power, we want it to equal not our source impedance, but the complex conjugate of our source impedance. And if these things are real, then the complex conjugate's the same thing as the source impedance, and we end up with our circuits 1 answer. And when this happens, then the P maximum average load, we have to talk about averages now, is going to be here's our voltage phasor. We're going to take its magnitude, we're not interested in its phase, and square it, and divide it by 8 times the real part of our source impedance. So that looks kind of like what we got up here, except instead of the 4, it's an 8. We had to take absolute values and reals to deal with the fact that these are now phasors. But why is this 8 instead of 4? I'm going to hand wave this answer a little bit and say why 8, not 4. It's because power is equal to 1/2 times the real part of V dot I conjugate. And it's that 1/2 is what's causing this to go from the 4 to the 8. Okay, just a quick thing, realize that here we're still measuring voltage in actual units of volts and not VRMS. If we did it in VRMS, instead of this being an 8, it would be a 4. Let me give an example.